video we're going to continue looking at pulleys and wedges, but we're just going to introduce friction into a couple of the questions. So what we're used to seeing is a kind of an arrangement like, hang on now, an arrangement like this, where we have some kind of particle on a surface. That particle is connected to another particle by a wire, and then the other particle is kind of hanging freely, like so. And what we first of all do when we solve these questions is we draw the force diagram. So let's say this particle has a mass of 5 kg and this particle has a mass of 10 kg. We're straight away going to assume that this particle is going to move down and this particle is going to move to the right. Because they're connected by a taut string, the acceleration of this particle A would be the same as the acceleration of this particle A. So when we solve these questions, the first thing we always do is we do a force diagram for each particle. So if we looked at the 5 kg mass, what we would usually do is we'd say, well, it's being pulled to the right with a force of tension T. And if we wanted to add the other forces onto it, we could say, well, its weight is mass times gravity, so 5 times g. And then its normal reaction force would be also 5 times g, because however much it's pushing into the table is pushing back up by that same amount, and that's why it doesn't move in the up-down direction. That doesn't happen. And this is all we've kind of done so far, because in all the questions we've done so far, what they've done is they've assumed that it's a smooth surface. And if it's a smooth surface, it means that there's no friction. But in reality, that's definitely not the case. If you get a book and you slide it along the table that you're sitting at now, you just push it and let it slide a little bit, it will stop. And the reason it stops is because there's a force acting against it. There's a force that's opposing its motion. And that force is known as friction. And friction always goes in the direction opposite the motion. So if the particle is moving to the right, like this, friction will be against it. Friction will be to the left. It's going to slow it down. And in real life, in everyday life, there's always friction. So what we're going to do today is we're going to introduce this friction. How do we include this into our questions? Now, the equation for friction, the equation for the amount of friction something has, friction is equal to mu times r. Now, mu stands for the coefficient of friction, and that looks like a U to you, but that's actually a Greek letter, and how you pronounce it is mu, M-E-W. It's kind of like a U with a little tail here. And R stands for the normal reaction force. Now, the normal reaction force in all of the questions we've done so far is going to be exactly the same as the weight. So if the weight is acting down here, like 5g, the normal reaction force, R, is the force which is opposing it. It's equal and opposite to it. So we'll talk about when the normal reaction force isn't the same as the weight, but in all the questions we're going to do today, it is. Now, mu is always between 0 and 1. So you could have, in the question, they'll usually give you a value for mu. Mu might be 1/2 or 0.5, or it might be 0.75 or 3/4, something like that. But it will always be between these two values. It will always be between 0 and 1. And 1 is a very high value of friction, and 0 is no friction, basically. So the higher the value, the greater the friction. The higher the value of mu, the greater the friction force. Last thing about mu is it has no units. It's a coefficient, so it has no units. So the best thing to do is kind of show you a question with this. So this is the 2001 ordinary level question. It's on page 7 of your booklet, and there's a solution there as well for you to look at. So here we have two particles of masses 18 kg and 9 kg respectively. They're connected by a light, inextensible, that end shouldn't be there, string, passing over a smooth pulley at the edge of a rough horizontal table. So the fact that it says smooth pulley, what that basically means is there's no friction between the string and the pulley here. That's where they're using the word smooth there. But they say rough horizontal table, and that means that between this particle and the horizontal table there's friction. The coefficient of friction between the 18 kg mass and the table is mu. The 9 kg mass hangs freely under gravity. The particles are released from rest. So when they're released from rest, we assume this is going to move down with an acceleration a, and this will move to the right with an acceleration a. The 9 kg mass moves vertically downwards with an acceleration of 5 over 9. So they actually give us the value of this. It's 5 over 9 meters per second squared, and this is 5 over 9 meters per second squared. Show on separate diagrams the forces acting on each particle and find the value of tension in the string. So the first thing we always do, even if they don't ask it, is do our force diagrams. So for the 18 kg mass, what forces are acting on it? Well, it's being pulled to the right by the string, so we've T for tension. Its weight is pulling it down, so that's going to be its mass times gravity, which is 18 times g. And because this is a flat table, the normal reaction force is also going to be 18 times g. Now, because it's on a rough table, there's also going to be friction slowing it down. And that friction is mu times r. Now, we don't know the value of mu, so we can say mu times r, which is mu times 18g. So that's the force. You could write that as 18 mu g would probably be a better way to write it. So that's all the forces on the 18 kg mass. 9 kg mass then is hanging freely, so weight is going to pull it down, which is 9 times g, it's mass times gravity, and tension is pulling it back up. Because this isn't in contact with a surface, we have no friction. So that's part 1 done. There are the two force diagrams. Find the tension in each string. Next thing we always do is we use our F4 equals ma equation, and you should be used to this at this stage. If this particle is moving to the right, it means that the T is bigger than the friction. So our resultant force equation will be T minus 18 mu g equals its mass, which is 18 times a. For this one, it's moving down with an acceleration a, so it's going to be the 9g force is going to be bigger than the T force, so it's going to be 9g minus T equals 9 times a. And the first question was to find T. So what do we know? Well, we know A is 5 over 9. We don't know mu. So if we're looking to find T, we have to use one of these equations, but the equation we'll use is this equation here. Because in this equation, we're looking for T, but we know A and we know G. So if I rearrange that equation, I get T equals 9g minus 9a. So T equals 9 times 9.8 minus 9 times 5 over 9. Value of gravity is 9.8 and the value of A, they told us, is 5 over 9. So put that into your calculator and you get an answer of T equals 83.2 newtons. Newtons is the unit force. And that's part 2 done. Last part then quickly is find the value of mu, giving your answer as a fraction. So we now know T, so we can now use this equation to find the value of mu. So it's going to be 83.2 minus 18 times mu times g equals 18 times 5 over 9. That means that 18 mu g equals 82.2 minus 18 times 5 over 9. And you can work this out yourself. 18 mu g equals 70. Sorry, that should be 3, shouldn't it? That should be 83.2. 73.2. And we're looking for mu, So to get mu, we're going to divide both sides by 18g. And we get mu equals 73.2 over 18 times 9.8. Put that into your calculator and you get 0.41. And because it's mu, there's no unit. There's no unit for the coefficient of friction. I use gravity as 9.8, so if you use gravity as 10, you'd probably get a neater fraction, but if you want to write that as a fraction, well, it's 41 over 100, isn't it?